Welcome back to the Deep Dive. Today we're diving into IBM's new Granite 4.0 family of open language models.
That's right. These models are really stirring things up, especially around efficiency for enterprise and even local AI.
Exactly. We've got the official tech overview from IBM, some competitive analysis, and, importantly, feedback from developers actually using these things.
Yeah, the real-world stuff.
Our mission today is to really get under the hood, understand the architecture, and figure out how it might change things, especially on limited hardware.
And it all really hinges on one core idea, doesn't it?
The hybrid architecture.
The hybrid architecture.
Yeah.
That mix of Mamba and transformer blocks, that's the heart of it. It's how they're trying to break free from some old limitations.
Okay, let's jump right into that then. Section 1. Decoding this hybrid setup. We're talking state space models, Mamba 2, specifically alongside traditional transformer layers.
Correct. And the mix is quite specific. Typically, it's a 9-to-1 ratio.
9 Mamba layers for every 1 transformer block.
Yep. So 9 Mamba 2 layers, then 1 transformer block repeated. The bulk of the heavy lifting, sequence-wise, is done by Mamba.
Okay, so for listeners maybe more familiar with attention, what's different about Mamba 2, this state space model approach? Why use it?
Well, think about standard transformers. It's like every word, every token has to check in with every other token simultaneously.
Right. The n-squared problem gets computationally very expensive very fast.
Exactly. It scales quadratically. Mamba, it's different. It works more like a conveyor belt. It processes the sequence linearly, one token after the other, and it keeps track of things in a hidden state.
Ah, okay. So double the text length, processing time roughly doubles, not quadruples. That linear scaling is the big efficiency win here.
That's the core idea. Mamba handles the global context, the long sequences, really efficiently because of that linear scaling.
But then why keep the transformer blocks at all? If Mamba's so efficient, why not go 100% Mamba? What does that 10% transformer part do?
Good question. It seems Mamba, on its own, might sometimes lack a bit of the nuance, especially for tasks needing very specific local context. Things like few-shot learning, where you give it examples right there in the prompt.
Okay.
So the sources suggest that periodically inserting that transformer block acts like a precision check. It forces the model to use that self-attention mechanism for a moment.
Sort of refocus on the immediate context.
Yeah, exactly. It helps integrate complex instructions or local details before handing the sequence back to Mamba for the efficient long-haul processing. It gives you that local precision.
Right. Efficiency plus precision. Makes sense for enterprise uses.
Yep.
Now, what about parameters? The bigger models, small h and tiny h, use mixture of experts, MOE.
They do, and it's a fairly sparse MOE setup. Small h, for instance, is listed as 32 billion total parameters.
Okay, 32 billion total.
But only around 9 billion are actually active during any given inference run.
And tiny h?
Even more sparse, 7 billion total, but just 1 billion active.
Wait, hold on a second. So if I'm deploying this, I download a 32 billion parameter model file, which is huge, but I only actually use 9 billion parameters when it's running. Isn't that a lot of dead weight storage overhead?
That's a totally fair point to raise. The storage footprint is bigger than a dense 9B model, no question.
So what's the trade-off? Why do it that way?
The key technical detail here seems to be IBM's use of shared experts. These are experts within the MOE structure that are always active.
Ah, okay. So not all the active experts are sparse.
Right. These shared experts handle the common foundational language stuff. This means the 9 billion active parameters are used really effectively. And it lets the other, sparser experts become highly specialized, maybe in tool use or code or specific RAD tasks.
Without needing to replicate the basic knowledge everywhere.
Exactly. It aims for higher quality from the active parameters, even if the total size on disk is larger. It optimizes for runtime efficiency and specialization.
Okay, that clarifies the MOE part. Now, this hybrid structure also leads to something else interesting. No positional encoding, or no PE in the age models. Why get rid of positional encoding? Isn't that crucial for knowing word order?
It usually is for standard transformers. Models using things like ROPE, rotary positional embeddings, need those explicit markers because attention looks at everything at once. Without them, order gets lost.
And that's often a bottleneck for context length, right? The PE itself.
Often, yes. But Mamba, because it processes sequentially, like reading.
Like the conveyor belt analogy.
Yeah. The order of the tokens is inherently baked into how it processes the data and updates its internal state. It knows what came before what.
So you don't need an external system like ROPE to tell it the order.
Apparently not. The state space model inherently keeps track. And removing that external PE constraint is a big part of why they can push context lengths so far, reportedly towards 1 million tokens in some variants. Pure transformers struggle to do that efficiently. All right, let's pivot from the architecture to the impact. Time for our neural signal check. Here's why this development actually matters at a technical level. This hybrid approach directly tackles that quadratic scaling bottleneck of pure transformers.
And the result is some pretty dramatic efficiency claims. The big one is reducing GPU RAM needs by over 70% compared to standard transformers,
Hmm.
especially for long context and batching.
That's the headline figure, and that 70% reduction isn't just a number, it translates directly into hardware costs and accessibility.
How so? Fewer expensive GPUs needed.
Precisely. When your memory requirements explode quadratically with sequence length, you're constantly chasing bigger, pricier GPUs, your H100s, your A100s, just to hold the context, the KV cache.
Right.
But if memory usage stays roughly constant regardless of sequence length, which is what Mamba enables, suddenly those massive RAG tasks, or analyzing huge documents, become feasible on more modest, maybe already existing hardware, mid-range GPUs.
It lowers the barrier to entry for complex AI tasks.
Dramatically. And that efficiency boost shows up in speed, too.
Yeah, the claim is up to 2x faster inference.
Up to 2x faster, yes. But maybe more importantly, the speed doesn't seem to degrade much as the context window fills up. That's a common pain point with transformers. They get slower as you feed them more context.
And community tests seem to back this up, people running it locally.
Yeah, we're seeing reports of pretty impressive speeds, like 50, even up to maybe 79 tokens per second, running on consumer-grade graphics cards, which is fast.
And speaking of local hardware, the memory requirements they list are, well, kind of mind-blowing.
They really are. It points towards real democratization. Take the tiny H model.
The 7B total, 1B active one.
Yeah. Quantized down to 8-bit, running 128,000 token context. It apparently needs only 8 gigabytes of RAM.
8 gigs. That fits on a decent gaming card, like an RTX 3060 12GB.
Easily. And then there's the micro H model, the 3 billion parameter dense hybrid.
Okay.
That one needs just 4 gigabytes of memory.
4. That's
Yeah,
Raspberry Pi territory.
exactly. A Raspberry Pi 8GB could potentially run this. A multi-billion parameter LLM running on hardware people use for DIY projects. It really changes the landscape for edge AI.
It's genuinely transformative potential. But okay, let's look beyond the official specs. What about trade-offs? The community feedback must mention something, right? If it's this fast and efficient, is accuracy or capability compromised anywhere?
That's the million-dollar question. And yes, some feedback hints at potential ceiling, especially when you push the context to its absolute limit, say, that full 128K tokens or even further.
What kind of ceiling?
While it processes all that data incredibly fast, some users have noted the output can get a bit spacier, maybe less precise, or prone to minor hallucinations when trying to recall very specific details buried deep within that huge context.
So it can read the whole book quickly, but struggles to remember the third word on page 500.
That might be a fair analogy, yeah.
Yeah.
It suggests that while Mamba is great at maintaining the long-range gist, maybe the sparse transformer layers have trouble perfectly integrating super-specific local details across such vast distances.
Interesting. So excellent for throughput, RG summaries, agentic tasks, but maybe not ideal for tasks needing extreme fidelity recall from massive contexts, like certain scientific or coding benchmarks.
That seems to be the nuance emerging from early user experiences. It excels where speed and long context handling are key, but the absolute peak of precision at extreme lengths might still be an area for refinement or comparison.
Okay, let's shift to the different model variants and their intended roles. The deployment footprint.
Right, they've got a few flavors. The small h, that's the 32 billion total, 9 billion active one, seems positioned as the main enterprise workhorse. For complex RAG, multi-tool agents, that sort of thing.
Heavy lifter.
Yeah, then you have the real efficiency stars, tiny h, 7B1B active, and micro h, the 3B dense hybrid.
The ones we just talked about running on low memory.
Exactly. These are explicitly built for low latency, running locally, running on edge devices. Think of them as fast components in a bigger system, maybe handling quick function calls for a larger agent.
Performing specialized, fast tasks.
Precisely. And then there's also a micro model, just micro, no H. It's a 3 billion parameter dense transformer.
Wait, a pure transformer? Why include that?
Seems like a compatibility play for Platforms are software stacks that haven't yet been optimized for the Granite hybrid architecture. It ensures broader usability right now.
Got it. A fallback, almost. Now, capability-wise, that small H model seems quite potent in agent tasks.
Yeah.
The sources mention strong instruction following.
Very strong. Reportedly outperforms nearly all open-weight models on the iFeeble benchmark, except maybe the very largest ones like Llama 4 Maverick.
And tool calling, function calling.
Highly competitive there, too. It keeps pace with much bigger models on benchmarks like the Berkeley function calling leaderboard. This is likely helped by its built-in support for structured output, like JSON.
Which is crucial for automation. And for IGE.
They seem to have optimized it for multi-turn REG. They've standardized how you pass in documents using specific documents tags in the system prompt. That kind of standardization is really helpful for enterprise integration.
Makes sense. And for coding tasks.
It supports standard fill-in-the-middle FIM using specific tags, FIM prefix, FIM middle, FIM suffix. Again, that clear tagging is good for IDE integration.
It all points to a focus on practical deployment in developer workflows.
Absolutely. And the efficiency makes that deployment broad. They list support for VLLM, LM Studio, Llama.
As long as it supports the Granite hybrid type, right?
Yeah, you might need the latest version of Llama, for instance. But maybe the most striking deployment option is the micro model running entirely in a web browser.
In the browser. How?
Using web GPU acceleration, it's apparently just a 2.3 Girobi download. That means you could prototype or run simple tasks without any backend infrastructure at all, just the user's machine.
That really lowers the barrier. Okay, let's talk competition. How does Granite 4.0 stack up against, say, Llama 3 or Mistral, just looking at the tech specs?
The most obvious differentiator stemming straight from that Mamba no PE design is context length.
Right, the potential for 1 million tokens with micro H.
Exactly. Compare that to Llama 3, which is generally around 128K tokens, or Mistral models, which are often in the 65K to 128K range.
So if your task involves truly enormous amounts of text legal databases, huge code bases.
Granite offers a technical path that others don't natively provide without adding complexity like retrieval augmentation on top.
Boy.
It can potentially just hold more context directly.
Beyond scale, any other technical advantages specifically for enterprise use? High compliance areas.
Well, the native tool calling support is a plus. Some other open models need more fine-tuning for reliable function calls, and the structured JSON output helps too. But then there's the licensing and governance aspect.
Apache 2.0 license, which is permissive.
Yeah.
But you mentioned cryptographic signing.
Yes, IBM signs the model checkpoints cryptographically.
What does that actually mean for a user, technically?
It provides provenance, assurance. For a business, especially in a regulated industry, being able to mathematically verify that the model file they downloaded hasn't been tampered with, that it's the genuine article from IBM, that's a significant technical guarantee for security and compliance audits. It builds trust in the model supply chain.
Okay, interesting. So summing up the core technical achievement, Granite 4.0 cleverly blends Mamba's linear scaling, giving it efficiency and long context capability with the transformer's precision for focused tasks.
And the headline result is that dramatically lower memory footprint, which crucially scales linearly, not quadratically.
It avoids the memory explosion.
Exactly. It really does shift the economics. Which brings us to our final provocative thought for you, the listener. Given this capability handling potentially up to 1 million tokens of context, with memory use that scales linearly and is dramatically lower overall, what really complex, memory-hungry technical jobs are now practical on mid-range, affordable hardware? Think full code-base analysis in one go, or ingesting enormous document sets for RAG without hitting that VRAM wall. Tasks that were basically locked behind the quadratic scaling bottleneck of pure transformers before.
What becomes economically feasible now that wasn't before? That's definitely the key question this tech raises for developers and businesses. A lot to think about.
Indeed.
And if you want to keep thinking about the technical details and implications of developments like these in AI and ML, be sure to visit our webpage at neuralintal.org and also check out our content over on YouTube. Thanks for tuning in.